Hello, I'm Norman Wahlberger, and welcome to this lecture on mathematics education and rational trigonometry, where we are now going to map out a new and better way of teaching young people trigonometry and a little bit more generally geometry. And the main orientation that I want to emphasize right now is this separation of what's currently one topic in mathematics into really two separate components. What we want to do is separate the triangle aspect of trigonometry with the circular aspect of trigonometry. Currently, these are all melded together in kind of a hodgepodge fashion, but logically they're actually quite separate topics. And it's much more efficient to view them separately and to develop each one independently. So to give you an analogy, suppose that in your backyard you have a lawnmower to mow your lawn and also a barbecue, to cook steaks. Now you have separate machines to do those things. You have a lawnmower, you have a barbecue. Wouldn't it be efficient if we could combine those two things and create a lawnmower / barbecue? One device that both mows your lawn and cooks your steaks. Well, this is probably not such a good idea. You really do rather want to keep these things separate. That's more efficient ultimately. Okay, it's a very similar story. Triangular measurement is really where the origin of the word trigonometry comes from. Combining the Greek letter for triangle, trigon, with the idea of measurement. And circular measurement, the study of the circles and angles and circular functions and inverse circular functions and all that stuff, is of course an important subject, especially when it comes to harmonic motion, but there's also a rational aspect of that as well. So we're going to try to push these two things apart, especially when we're viewing the educational aspect, and we're going to say, well, how would we best just approach this subject? And then later on, how would we approach this subject? And perhaps these two different ingredients in this topic will be viewed differently or even separately. Okay, so this is a very powerful, different orientation to how we teach this fundamental subject to young people. So just to make sure we're all on the same page, let's review some basic facts about triangle measurement before the 17th century kind of revolution. Now, when we look back at the history of trigonometry, there's a kind of a practical aspect and there is a sort of theoretical aspect. The practical aspect starts where we're concerned with measurements, and often they're linear measurements that we're interested in with a ruler. For example, we have a ruler and we're actually interested in making measurements with our ruler and deducing certain unknown quantities from other ones, for example. Okay, so that's a very natural thing to want to do practically. However, the story with pairs of lines, or say vertices, where two lines are coming together, or sometimes called an angle. So sometimes this configuration itself is called an angle. We talk about that angle, that configuration of two lines meeting at a vertex. So measuring the separation there is something that historically goes back long before angles. Okay, so before the actually Seleucid Babylonian astronomers introduced angles, and then the Greeks also around 300 BC, 400 BC. Before that, people were also studying separations, but they were doing it in a very different way. So if you go back to the ancient Egyptians, or in fact the Babylonians as well, you find that they were interested in inclinations of ramps and pyramids and things like that. And the way they measured such an inclination was through something very similar today, what we call a slope. Okay, so what you do is you draw a right triangle there. And because of the beautiful similarity properties of right triangles, it doesn't really matter where you drop that perpendicular. Okay, so now you have a triangle. And so you have three sides. You have maybe a base, and maybe a height, and maybe a hypotenuse. All right, so we can give those sides some names. So those would be like lengths, okay, measured on a ruler. And then you could describe the inclination of this inclined plane by a ratio of two of these sides. And you have some choice as to which ratios you want to choose, because there's 3 quantities, and so there's actually 6 sort of possible choices. But the one that the Egyptians liked is the reciprocal of our slope. So our slope, it would be a delta y over delta x, it would be a h over b. But they prefer to think in terms of b over h. Okay? So the ancient Egyptians called this the seked, and they described the inclination or steepness of pyramids by this quantity here. It turns out that the Babylonians also used this quantity. So this is a measurement of the relative positions of these 2 lines, which is ratio-based and not angle-based. Okay, and it actually precedes by at least 1,500, probably 2,000 years, the angle-based story that came much later. Then on the theoretical side, which is really encoded by Euclid, Euclid was the great theoretical Bible of geometry, we have a different point of view. So Euclid avoids using a ruler. That's not part of his tool chest. A straight edge, yes, but a straight edge made it into a ruler, no. All right, so he's not talking about this length and this length and this length. He's never doing that. What he does rather is he measures segments by areas. Okay, so this is the Greek process called quadrature, where basically you create squares built on sides. So if we want to measure that side, we build a square, and then we measure the area of that square. Okay, and so Pythagoras' fundamental theorem is, for Euclid, a theorem about 3 areas. The areas of squares built on a right triangle, satisfying this crucial relation with what we call now quadrances. Okay, and in terms of angles, well, he also does not invoke the Babylonian angle measurement of degrees. He refers to angles as geometric quantities and talks about comparing them. So by that he means that we can kind of allow ourselves to translate or move an angle, a rigid configuration, to another place. So we could say that this angle is the same as that angle, by which he means not that they're measured to be the same, but rather that we could transform one on top of the other. Okay, that's his understanding of equality of angles. And angles, in his sense, means this actual configuration consisting of 2 lines. So theoretically, Euclid is avoiding distances, and he's avoiding protractor use of angles as measured in degrees. So very important to understand that this was the orientation of people to sort of theoretical geometry. But then later on, practically, trigonometry started to develop once astronomy came into being around 300 BC, and then angles started to play more of a role. But originally, they really were not there. They're not part of the original story of trigonometry. All right, so then as we move closer to this pivotal 17th century, something really dramatic changes with the introduction of Cartesian coordinates due to Fermat and Descartes and others. So this really transformed our understanding of geometry and what was possible and how to enunciate various things. So what's not perhaps appreciated these days, however, is that a Cartesian coordinate system like this introduces non-homogeneity. So it takes what is formerly seemingly a homogeneous situation, like a blank page, looks the same in every direction. You can't tell if you rotate it or translate it. It's just a blank page. But once you introduce a coordinate system, then things change, because now you have a preferred set of directions. You have a horizontal, you have a vertical, and measurements are made with respect to this fixed coordinate system. Now that subtly changes things. You may not want it to change, but it does change things, okay? And it's perhaps not even really appreciated these days just how extensive and significant the change is to going from that Euclidean framework of an empty page to this Cartesian framework of having fixed coordinate axes. Okay, so one of the implications here is that the notion of distance as measured by a ruler, naively. But when we are trying to get at that from a Cartesian coordinate point of view, the distances along the horizontal or vertical directions are fine because we have these coordinates here. And so if we want to know the distance between these 2 points, well, it's just a question of taking a difference between coordinates. So distances along here are fine, distances along here are fine, but distances along non-horizontal or vertical directions are not always fine. In fact, generally they're problematic. And that's because, well, the Pythagoras' theorem in this context is only really allowing you to access the square of the distance. In other words, the quadrants or the area of the square that you build on a segment. That is a thing that the Cartesian coordinate system is giving you naturally and giving you simply and coherently, and you can compute it. But to get a so-called distance, you have to take this square root. This is the rock on which all these ships founder, right? You can't actually take these square roots in general to complete infinite precision. And so you end up having to distort your understanding of what's really going on by pretending that you have square roots that you don't actually have. Okay. So distance becomes problematic in the Cartesian coordinate system, necessarily so. And correspondingly, angles also become problematic. They also become almost completely incommensurable with Cartesian coordinates. Again, this is not something that's acknowledged, not something that's explained to young people, because we don't want them to realize that this new system, despite its advantages, has serious disadvantages also. And I've explained this, for example, here, 2 over 1 over, finding that angle is something that you can't actually do precisely. And that's not special about this. It's sort of typical. Typically, you have 2 lines expressed in this kind of system. You ask what is the angle between them, and you cannot answer that question. You just cannot answer that question. You can do so approximately, but if you want to stay in a theoretical, in an exact framework, you are lost. The game is kind of over. So this is a very serious problem that, unfortunately, mathematicians, wanting to embrace this great Cartesian coordinate system for lots of things, in particular analysis and calculus, they don't really acknowledge it. It's a kind of a hidden blemish, okay, or a shadow upon the whole theory. Note, however, that slopes are quite good. Right? Finding the slope of such a line, in other words, going back to the pre-angular trigonometry of the Egyptians or the Babylonians, is easy. Delta y over delta x. The Cartesian coordinate system is just designed to make such a thing very easy. And that's, of course, very convenient for calculus, because in calculus we measure inclination of lines, not with angles typically, but with slopes. Okay, so for that, the Cartesian coordinate system is very convenient. But there's an incommensurability there, right? The slopes are working, the angles, quite honestly, are not, or only approximately. And that's a very big difference. All right, so now let's turn our gaze towards rational trigonometry. What does it accomplish? Why is it superior to the standard point of view? Why does it offer huge new potential benefits to mathematics education? Well, the heart of the matter is because rational trigonometry works within the algebraic Cartesian coordinate system. It is aligned with Cartesian coordinates. It does not fight against it. It uses and glorifies in the algebraic aspect of the Cartesian coordinate system. So we're working with the coordinate system here and not against it. Okay, here is that same configuration that we looked at before. A point A here, a point B here. We're looking at this segment. We're trying to get some understanding of how big that segment is, how far apart those points are in some sense. And we know now that the crucial quantity is the quadrants. Right? The quadrants is the algebraically correct way of thinking about how far those points are separated. And what is the quadrants? Well, it's the x squared plus the y squared. It's 2 squared plus 1 squared, or 5. And geometrically, that's the area of the square built on the segment. So we're going exactly back to Euclid's orientation towards measurement of segments. This is not some newfangled thing. This is going right back to Euclid. So quadrants is algebraically the right notion, and this way we get an algebraic approach to Pythagoras' theorem that really can be completely established in an algebraic setting without any real numbers, without any approximations necessary, without having to invoke algorithms that ostensibly go on forever to compute square roots. Just a night and day difference, okay? It is definitely the right way of thinking. So the quadrants is algebraically the primary quantity, and then the distance is the square root or approximate square root of a quadrant, which can be quite useful in practice, in applied settings, fine, but it's not the primary object mathematically. The quadrants is primary, the distance is an applied quantity which is secondary to the quadrants. It's the approximate square root of the quadrants. So we're working inside the Cartesian framework here. We're really working in an algebraic setting. And so everything is much more pleasant and easy, in fact. For students too. In fact, especially for students. And now what about this rational trigonometry replacement of angle? The notion of spread between two lines, which is kind of the critical new innovation. Well, the spread between lines, or in fact vectors, is again completely algebraic. Right? We are not fighting against the Cartesian coordinate system. We are adapting our metrical structure so that it works entirely within the algebraic framework of Descartes and Fermat. So what is the spread? Well, first of all, in just the Euclidean setting, like before the 17th century, we can express the spread between these two lines by drawing a right triangle, much as the Egyptians would have, or the Babylonians, and then looking at a ratio. But instead of a ratio of distances, we prefer a ratio of quadrances because that's more accessible to us. And well, which ratio it is? Well, it turns out that this is the ratio that we use for the spread. It's the opposite quadrants divided by the hypotenuse quadrants of such a right triangle. So S is Q over R, this quadrants over this quadrants. So that's how we think about it geometrically in the context of Euclid. Euclid would have said, yes, this is a reasonable and legitimate notion. Why didn't I think of that? Now, in the Cartesian framework, there's also a very nice and elegant way of thinking about it. And we don't have to go outside the framework. We have two vectors, u equals ab, v equals cd. We're interested in the spread between these two vectors, or the spread between the corresponding lines that they generate. What's that spread S? Here's the formula that you all know by now very well. 1 minus this dot product, AB dot CD, all squared over the quadrants of u, which is a squared plus b squared, times the quadrants of v, which is c squared plus d squared. And this dot product is the usual familiar one, the Euclidean AC plus BD. And if we like to, we can rewrite this due to this pleasant alternative formula so that we get an AD minus BC squared on the numerator there, and then the denominator same as before. Crucially, this is algebraic, it's rational. If these are all rational numbers, then this is a rational number. If these are all over some finite field, then this will be over that finite field. Okay, it's a very flexible notion. And if we want to have some practical device that allows us to sort of read off what a spread is, well, we can use Paul Miller's protractor, which I've discussed in Math Foundations 142 to 145. A very beautiful little device that was discovered by a viewer, Paul Miller. And here's a way we can frame that. It uses a circle. Okay, so here's a circle, and here's a diameter of that circle, and the diameter is labeled just linearly with entries 0 up to 1. So that segment is labeled 0, 0.1, 0.2, 0.3, etc., up to 1. And at this point here is where we are going to measure spreads. Spreads against this horizontal line, which is that diameter, and some other line. So here's some other line, and we're interested, what's the spread between this line and this line? Well, Paul Miller says, well, just take this line and see where it meets the circle. Okay, it meets the circle at some point, and then go straight up to the diameter and read off the coordinate of that diameter. In this case, that would be 0.3. That's telling us that the spread is 0.3. Notice that this is a bit like a protractor in that it uses a circle, but crucially we do not have to separate the boundary of the circle into equal pieces. We only have to separate the diameter into equal pieces. That's like night and day difference. Okay. It is very hard to separate the circumference into 90 or 180 equal pieces. It's not hard at all to separate the diameter into 10 or 100 pieces. So this is a much simpler and much more elementary kind of protractor that measures spread. It shows you that spread is very simple kind of quantity. You can just read off what a spread is very simply. Okay, suppose you do want an angle instead. Suppose you got that spread and you want an angle. What do you have to do? Well, you have to do something which is more or less something like this. You have to take a square root of the spread, and then you have to apply some inverse circular function. So if you take the arc sine of the square root of this, get your calculator to spit out something, then it will give you an angle in radians. And there's really no simpler way. Given two vectors, you really have to do something like this. That's just the way it is. So it's much more complicated, and you can see that it's a secondary quantity. First, you have to effectively calculate a spread, or maybe the cross where you don't have the 1. And you have to take a square root. That's something you can only do approximately. And then you have to invoke a circular inverse function, which you can only do, again, approximately with the aid of a calculator or computer. So hugely more problematic to extract an angle from such a situation. The spread is the natural thing. The spread is the simple thing. The spread is the algebraically beautiful thing. That's rational trigonometry. It's just massively simpler and better than standard trigonometry. And now, once we realize that and say, yes, that's correct, we have huge now opportunities for rethinking mathematics education. This is so exciting. We can now take our understanding and actually go into the classroom and say, guys, let's do things differently. Let's do things better.